On the basis of either of these two F statistics, we would conclude that the variances for women and for men are not equal, and consequently the t-test we calculated here is not strictly appropriate. In order to calculate the appropriate t-statistic, we must use the formula on page 291, 9.10, and I'll calculate that t-statistic here. I'm going to clear this, and I'm going to calculate the new t-statistic. It is equal to the mean for women minus the mean for men divided by the square root of the variance for women divided by the appropriate sample size value, which is 34 for women, plus the variance for men, again divided by 34. And when I hit enter, I get, surprisingly, the same value. So what is the point of using this t-statistic versus this t-statistic? In a case where we have equal sample sizes, we have 34 women and 34 men, the t-statistic calculated in this way will be exactly equal to the t-statistic calculated in this way. But if we have different group sizes, these two t-values will not be the same. There's another important point to consider in regard to unequal variances, and that is that this probability that was calculated for the equal variance case is no longer correct. The reason is no longer correct is that probability says there are 66 degrees of freedom, or 33 degrees of freedom for the women and 33 degrees of freedom for the men. The true probability for unequal variance comparisons is always less than n-1 for one group plus n-1 for the second group. The actual formula, which is used by Excel to calculate degrees of freedom with unequal variance, is probably the formula given in 9.12 on page 292. I say probably the formula because there are a number of different formulas for calculating degrees of freedom with unequal variance, and this formula seems to come closest to replicating the value of degrees of freedom that Excel actually calculates itself. How does that Excel calculate those degrees of freedom? Well, let's go back to Tools, Data Analysis, and this time, instead of taking t-test 2 sample assuming equal variance, we're going to take the t-test 2 sample assuming unequal variance. And when I say OK, I'll select the first variable range, women, Control-Shift-Down arrow, and I'll select the second variable range, men, Control-Shift-Down arrow, hypothesized mean difference. There are labels in the first row, and the output range will be, this time, right here. When I say OK, I get this result, and you can see that the t-statistics are exactly the same, but an important difference is this 39 degrees of freedom. In this case, we said there were 66 degrees of freedom, Excel has decided that because of the unequal variance, there are actually only 39 degrees of freedom. And what does this do to probabilities? It doesn't change them very much. This is the two-tailed probability. But it does change them slightly. In general, if you have unequal variance, as shown by the F-test, the two-sample assuming unequal variance add-in is the appropriate add-in because it calculates the appropriate degrees of freedom. But when you have equal-sized groups, you will almost never make a different decision using the two-sample assuming unequal variances versus the two-sample assuming equal variances. I won't demonstrate this in this video, but if you have unequal sample sizes and the F-test indicates unequal variances, you must always use the two-sample assuming unequal variances t-test.